developed and manufactured a machine for that. You can do friction welding by using milling machines, des fraiseuses. On peut utiliser les fraiseuses pour faire le soudage par friction ou par contact, mais pour faire quelque chose de précis, il faut des machines précises, and you have to have rigid machines that can do friction, because there is a lot of pressure, there is a lot of heat, and you need to have special machines. And Professor Bukharola was able to design, his team was able to design and manufacture this machine and use it. You will see that it is very interesting from what I have seen yesterday from his laptop. If we can get it working, inshallah. After this presentation, which will be only 15 minutes, Professor Bukharola.
Okay.
After this presentation, we'll go for coffee break. Then you will take off.
Donc je vais parler en français. Donc je vais présenter un travail de deux doctorants qui sont là, Arzour et Jabbar Hassan. Ce travail est effectué en collaboration avec l'université de Schleuf et de l'Université. Donc on a intitulé ce travail-là l'évolution de la microstructure. Oui, l'évolution de la microstructure durant un soudage par friction sur un acier de la série AISI 316. En réalité, ce n'est pas le soudage par friction lui-même qui nous intéresse, mais c'est les effets induits par ce procédé de soudage. Donc, je vais rapidement présenter le laboratoire de mécanique avancée de l'UCHP, lequel je préside. Donc, il a été créé en 2001. Il est composé de 4 équipes. Donc, les deux premières équipes travaillent dans le domaine de la fiabilité des structures et comportement des matériaux. Pratiquement, on travaille sur tous les matériaux, ça va du béton jusqu'au composite, les aciers, les aluminium, l'aluminium. Et on a deux autres équipes qui travaillent dans le domaine de l'engineering. La troisième équipe travaille sur la maintenance et l'isolation vibro-acoustique. Et la quatrième travaille dans le domaine des dynamiques des systèmes multicouches. Donc, l'effectif de notre laboratoire au 31/12/2015. On a 19 chercheurs confirmés, 5 professeurs de conférence classe A, 6 maîtres de conférence classe B. On a 22 doctorants inscrits au laboratoire, ce qui fait un effectif de 41 membres. Donc, on a deux formations en master, mécanique de construction et technique de fabrication mécanique. On a une formation doctorale qui s'intitule mécanique, fabrication et fiabilité mécanique. Et on organise chaque année 4 séminaires pour les doctorants de notre laboratoire. 2 séminaires dans lesquels eux exposent leur état d'avancement et 2 séminaires, on ramène des personnalités scientifiques pour animer ces séminaires. Par exemple, le deuxième séminaire qui s'est déroulé le 26 novembre à l'UCHP. Donc les doctorants, ils ont exposé leur état d'avancement et on invite toujours dans ces séminaires dans lesquels les doctorants exposent une personnalité qui parle d'une thématique. Par exemple, le deuxième, on a invité le professeur Kermia Mohamed de l'UCHP et il a parlé de l'utilisation de l'énergie renouvelable. Le prochain séminaire, si ça vous intéresse, vous serez les bienvenus. Il sera organisé le 17 décembre 2016 et portera sur les techniques de CND et va être animé par un professionnel qui s'appelle Yemeni. Donc c'est un professionnel, il a travaillé au Moyen-Orient. Il a une entreprise à Alger. Il travaille beaucoup avec son FRACT, donc, je continue. On a un certain matériel ou équipement au niveau de notre laboratoire. On a une machine de fatigue conventionnelle de capacité 25 kN. On a une machine de fatigue par choc qu'on a fabriquée. Je vais vous la montrer. On a une machine de soudage par friction qu'on a fabriquée par nécessité. Et on a d'autres moyens plus légers. On peut faire le traitement thermique, c'est-à-dire on a des fours qui montent jusqu'à 1200 degrés. On peut faire de la microductée, on a de l'appareillage. On peut faire des observations spectroscopiques, même un maillage. On a 3 licences. On a une licence professionnelle du SolidWorks. On a une licence logicielle de calcul constant. Et on a une licence de matelas. Donc, voici la machine qu'on a construite. C'est une machine de fatigue par choc. Elle est instrumentée. Donc, généralement, on fait des essais de choc sur des plaques. Donc, par exemple, ici, c'est une plaque encastrée sur deux côtés, libre sur l'autre. Et on fait des impacts répétés avec la même énergie. Donc, on a, là, ici, c'est l'impacteur. On peut le changer. Il peut être sphérique, demi-sphérique, pointu. On peut changer, par exemple, le diamètre, ainsi de suite. Là, c'est le compteur de cycle, là, c'est le capteur de déplacement et on enregistre sur l'oscilloscope le signal de chargement. Donc, après, on fait des essais derrière, post-impact, par exemple. Là, c'est les essais de compression. On fabrique tous nos montages d'essais. On n'achète jamais les montages d'essais. On les fabrique, on les conçoit, on les fabrique chez nous. Ça, c'est un montage pour faire de la compression. Donc ça c'est la plaque initiale, on coupe autour de l'impact une petite plaque, c'est celle-ci. Après on fait des essais de compression pour quantifier la rigidité et la résistance résiduelle de cette plaque impactée. Donc ça c'est la machine, la deuxième machine sur laquelle on fait nos soudages, nos opérations de soudage. C'est une machine qui a été conçue et fabriquée à 100% au laboratoire. Donc elle est composée d'un système mécanique, système électrique, vous avez le moteur, le frein, vous avez les mandrins dans lesquels on fixe les échantillons qu'on veut souder, vous avez un groupe hydraulique, donc par pression, donc on applique deux types de pression, une pression de forgeage et une pression de friction, et vous avez la partie électronique, c'est-à-dire la commande. Donc elle est complètement automatisée, et sur ce pupitre-là, vous allez voir, on règle certains paramètres nécessaires au soudage. Je vais essayer de vous montrer la vidéo. Dommage. C'est pas grave. Donc, on travaille sur toute la gamme de la série AISI, c'est une série américaine, c'est de l'acier inoxydable. C'est un acier très résistant à la corrosion, mais il est très délicat en même temps. Donc, ça, c'est au général, c'est ses propriétés mécaniques. Certaines, c'est nous qui les ont déterminées. Et ça, c'est les propriétés juste quelques mots sur cette nuance, c'est-à-dire bien les aciers austeniques. Donc, par exemple, le 357, je m'en ai caractéristique métallurgique principale, il est riche en chrome et en molybdène. Sa composition chimique contient 5 éléments gamma-gènes. Les gens qui travaillent dans. Donc, c'est un matériau très délicat. L'élaboration, il faut faire très attention parce que ces éléments-là peuvent élargir le domaine ferritique, par exemple. Ces éléments-là peuvent aussi élargir le domaine austenitique. Et en élaboration et en service, on peut avoir des surprises. Par exemple, la présence de la ferrite résiduelle ou la transformation en intensité par refroidissement ou par déformation peuvent influencer beaucoup sur l'austénisme. La ferrite, elle a parlé déjà hier de ce problème-là, pourrait apparaître sous forme des bandes parallèles à la direction du laminage. Voilà. C'est les bandes de la. Donc, malgré que ça peut être un avantage comme ça peut être un inconvénient. Par exemple, pour la soudabilité, c'est un avantage. Par contre, pour la durée de vie, c'est un inconvénient. Donc, ces bandes de la ferrite altèrent fortement la durée de vie du matériau. Ça fonctionne. Voilà, ça marche. Voilà, vous avez quelques aspects physiques des pièces soudées. Voilà. Je vous montre 3 exemples qui ont été soudés par différents paramètres. Là, c'est le nombre de coups, 30 newtons par minute, le temps d'accostage. Vous allez voir sur la figure. Ça, c'est la pression de friction. Ça, c'est le temps de friction. Ça, c'est la pression de forgeage. Et ça, c'est le temps de forgeage. Ça, c'est la consommation de la matière lors du soudage pour la formation de ce beau relais. Et ça, c'est les températures maximales atteintes lors de l'opération de soudage. Et ça, c'est la vitesse de refroidissement, c'est la vitesse de l'élévation de la température jusqu'à la température maximale. Voilà, vous avez un graphique ici de l'opération de soudage en température. De ce point-là, c'est la première phase. L'opération de soudage est composée de 3 phases. L'accostage, la friction jusque-là et le forgeage de E3 jusqu'à E4. Donc, quand on démarre la rotation d'une partie, par exemple celle-ci, elle est fixe, elle pousse. Donc, on est à la température de la chambre. 23-24 degrés. Et, donc, après, on a l'élévation de la température jusqu'à la température maximale. Une fois qu'on arrive à la température maximale, le matériau est porté à l'état pâteux. Donc, ça continue à tourner et pousser. Donc, le frottement diminue. Donc, automatiquement, la température va chuter. Donc, elle va chuter jusqu'à la fin de la phase de friction. Donc, quand vous êtes en train de souder, quand vous êtes en dessous à ce sommet-là, vous voyez voilà, ce flux de chaleur. Donc, entre ce point E2 et E3, c'est là où on aura la diffusion de la température. Donc, vous aurez le grossissement du grain. Entre le point E1 et E2, vous en avez un affinement du grain. Donc, et quand on arrive ici, on arrête, on stoppe. Donc, il n'y aura plus de rotation. On va injecter une autre valeur de pression de forgeage, qu'on appelle la pression de forgeage, sur un temps donné, pour faire évacuer la matière pâteuse vers l'extérieur et former définitivement le beau relais. On comprend bien que le beau relais commence à se former entre le point E2 et E3, et sa forme finale, elle le prend entre le E3 et le E4. Donc, si par exemple, je regarde ce qui se passe ici, voici l'aspect physique du cordon de soudure. Si je regarde maintenant la microstructure, la microdureté, c'est celle-ci. Donc, ce que vous voyez ici, la ligne, c'est la moyenne de la microdureté du métal de base. Donc, on comprend bien que la microdureté, elle a augmenté. Donc, on a un affinement du grain et une augmentation des propriétés mécaniques de votre matériau. Si on arrive maintenant à la fin de la phase de forgeage, de friction, pardon, avant de commencer le forgeage, voici, on voit bien qu'on a commencé à former le beau relais. Et à ce niveau-là, si je regarde la micro-dureté, c'est la rouge, on voit bien qu'il y avait un grossissement de grain et la micro-dureté a fortement chuté. Et si je continue maintenant, si j'arrive jusqu'à la fin de forgeage, c'est-à-dire à la fin de l'opération de soudage, le bourrelet, sa forme, elle augmente, c'est-à-dire la consommation de la matière, elle augmente. Et si je regarde qu'est-ce qui s'est passé au niveau de la microstructure, je constate que la partie rouge, qui représente la deuxième, voilà, la microstructure, elle a augmenté. Et le phénomène qui se passe ici, c'est cette formation de ce qu'on appelle, nous, le corps dur. C'est-à-dire, là, on est en présence d'un petit noyau qui a des propriétés fortement hautes et avec des grains fins, mais en dehors de cette partie-là, on a pratiquement un joint soudé, ou bien un joint qui a pratiquement les propriétés de la matière de base, ou bien proche à la matière de base. Ça, c'est la comparaison entre deux conditions de soudage. Souvenez-vous, dans le tableau, on a montré X2, X4, X5. X5, la température max, c'est de l'ordre de 819 degrés, et X4 est de l'ordre de 870 degrés. Donc, plus la température max augmente, plus la largeur du corps augmente, et le pic, il est élevé. Donc, la question, ou bien le problème qui se posait à nous, quand on était en présence de ce phénomène, comment je peux supprimer ou diminuer l'effet de ce corps? Parce qu'ici, vous en avez une microstructure qui est différente à celle-ci. Donc, voici visuellement le corps. Donc, c'est une macrographie et le corps, on le voit bien ici. Et donc, son diamètre est de 3 à 4 mm. Donc, voici la micrographie optique de métal de base. Par mètre, là on voit bien les plaques de l'Austenitic, et après soudage, on voit bien que les plaques de l'Austenitic sont fortement déformées. Ce que vous voyez ici, c'est l'interface du joint. Et là, c'est le canal avec lequel, ou bien à partir duquel, on a l'évacuation de la matière quand on soude, quand on ramène la matière à l'état pâteuse et on déclenche la pression de friction et de forge. Ok. Voilà. Donc on peut faire. Donc en réalité, on a fait une batterie de vérification, par exemple de DX ici, pour vérifier est-ce que les éléments alliés principaux de la matière ont bougé ou pas. Là, on constate qu'on a une très bonne répartition, comme celle de la matière de base. On peut faire des essais de traction. Là, qu'est-ce qu'on constate? On constate quand on soude, on n'altère pas réellement les propriétés mécaniques comme la limite élastique et la limite à la rupture, mais on diminue fortement la ductilité. Et ça, c'est dû à ce fameux corps qu'on fabrique ou bien qu'on fait naître au niveau de l'interface du joint soudé. Donc, ça, c'est l'aspect physique de la rupture. On constate bien que c'est une rupture ductile. Ça, c'est une image nette. Le corps, vous le voyez ici, le voilà. Donc, quand on a fait cet essai de traction, donc, la fissure, elle naît ici, elle se propage dans cette partie-là, et après, ça, c'est la partie de la rupture brutale. Donc, ça, c'est la micrographie même de ce corps-là. On constate bien qu'on a un grain fin au niveau de cette zone-là. Voilà, je vais terminer. Donc, on a repris les travaux, mais je ne vais pas vous dire comment, mais là, on constate sur le range-là qu'on n'a pas de corps. On n'a plus de corps. Donc, la soudure, elle a pratiquement les mêmes propriétés que le matériau de base. Je vous remercie.
Thank you, Professor Kokaroba. And if you allow me, we are not going to take any questions because we are running out of, actually, we have a 30 minutes delay in our morning session. We are going to go for break. You can ask questions to Professor Kokaroba during coffee break. And we are going to reduce the coffee break from 30 minutes to 20 minutes in order to catch up.
Plasma welding and Carmine's presence on the appearance of cracks and microcracks. The idea behind this paper was to analyze the behavior of cracks that occur during plasma welding of a machine part. Hard facing is a process that was generally used in order to apply an additional layer which would protect against negative effects such as wear, corrosion, and erosion. These effects would typically lead to a loss and to reduction and loss of dimensions of mechanical parts, which would then have to be replaced. The original purpose of hard facing was to be used as a means of repair such dimensions, which in some cases would eliminate the need for replacement and would lead to considerable savings. For example, as in case of one of our experiments with the crane wheel from Železara Smederevo, where repair welding technology was applied, and it turned out that this made the savings of around 60%. However, recently, the application of hard facing extended to protection of new machine parts and tools by means of applying new layers that would significantly improve certain properties. In the case of this paper, the goal was to increase the hardness so that the wear resistance would be improved. Now, improving of surface characteristics represents a specific technological problem which involves considerable knowledge about the following factors: material science and mechanical properties of both parent material and the weld metal, especially in cases where there are significant differences in these mechanical properties. These factors are important due to the fact that during hard facing and other techniques for improving of surface characteristics, cracks and microcracks will always occur, and they can have a significant effect on the machine integrity, especially in cases where they start propagating under certain conditions. When it comes to hard facing, crack initiation represents a considerable problem, especially in cases when hardness needs to be improved and when hard materials are used. Cracks in these cases are inevitable and will always occur, but there is also an additional possibility of them propagating from the welded material into the parent material. Because of this, the welding technology for hard facing should be selected carefully along with the additional materials that will be used for the welded layer, since machine parts which are usually hard face can have many different functions and are subjected to a wide variety of loads. And alloying elements used in the additional material play a very important part in the behavior of the material. Now, in order to increase the wear resistance of a machine part, additional materials typically should have a high carbide content, which will improve the hardness of the welded layer significantly. However, the presence of carbides, in our case tungsten carbides, also increases the risk of cracks occurring and propagating through these carbides. In this paper, we will present an example of hard facing of a tooth of a marble milling machine, where the goal was to weld an additional layer with a thickness of 6 millimeters on top of an existing tooth in order to improve its hardness and therefore wear resistance. Hard facing in general represents the process of creating an inseparable connection between the parent material and the welded layer by means of melting and softening, which of course leads to microstructural changes and the appearance of cracks in both materials. Now, before the hard facing process can begin, the following activities need to be undertaken. First of all, as we mentioned, the method for hard facing needs to be carefully selected. Then, if there is necessity, preheating should be performed. Next, we select the additional material and apply the bonding layer. Following this step is the determining of the number of passes and layers for the welding and the determining of technological welding parameters such as amperage, welding speed, and angle. In case there is need, additional heat treatment is performed as well. The hard facing technology that was used for this paper is also known as plasma welding. Plasma represents an electrically conductive, dissociated, and highly ionized gas which is created inside a device called plasmatron and serves the purpose of an electric arc. Plasmatron receives its power from direct current and consists of an electrode which acts as a cathode, then a nozzle, copper nozzle, or the workpiece, which acts as the a node and an isolator between them. The power that is supplied at plasma welding, the copper nozzle narrows the advantage of plasma welding over some more conventional procedures such as tungsten inert gas welding is in that it achieves higher temperature with better temperature distribution, although at the moment I cannot remember how exactly. And now, well, the important aspects for plasma welding is the gas that is used. When choosing the gas or a mixture of gases, one should have in mind the atomic and specific masses, as well as the thermal conductivity coefficient, which is of great importance when selecting the plasma gas. Also, it is preferred for these gases to have lower values of ionization energy. Normally, pure argon is used for plasma gases with a very high argon content. You see, because it has many advantages. It is inert, so it doesn't react with other materials, it doesn't cause metallurgical problems, it has low ionization energy, and of course it is cheap. Applying of a protective layer to the tube by plasma, in this case, was performed using eutectic Castelline equipment, and in this case, pure argon was used as the shielding gas, whereas the plasma gas consisted of a mixture of argon and hydrogen. Here, you can see the alloy which was used as an additional material and is made of a niobium, boron, silica, iron alloy with a very high tungsten carbide content of 60%. Because of this, the surface layer formed by the powder can achieve hardness of up to 60 HRC. And here you can also see what the equipment that was used looked like. So as I have mentioned, the goal was to create a welded layer with a thickness of 6 millimeters on the tooth in order to increase its wear resistance. Once the hard-facing process was complete, the structural and microstructural analysis of the welded layer zones were performed. And this was achieved by cutting the tooth model in half, but that will be explained a bit later. The idea was to analyze the effect of plasma welding on an experimental level to see how the cracks where the cracks are initiated and how they are distributed. So the most important aspects that were researched here were the thickness of the welded layer and the distribution of the cracks, especially in the microstructure. The parent material used for the tooth was 25 chromium molybdenum 4 QT steel, according to DIN standard. The QT designation stands for the fact that it was delivered in a quenched and tempered state. It is a low-alloyed, heat-treatable steel with good weldability, and its tensile strength typically ranges between 700 and 950 megapascals. Such materials are usually used in automotive and aircraft industry for components which require high toughness, such as axles, axle journals, turbine parts, rotors, etc. This steel typically has a hardness of around 20 HRC, which, as you can notice, is significantly lower than the hardness of the welded material. Here, you can see the chemical composition of the parent material with the content of carbon, silica, manganese, phosphorus, sulfur, chromium, and molybdenum. As it was mentioned previously, in certain cases there is a need for preheating before the hard-facing process can begin. Such was our case, and the workpiece was preheated using gas flame, and the preheating temperature was determined to be around 130 degrees Celsius. The number of passes for the plasma welding was determined to be 7, and each pass contained 3 layers. The passes were 20 millimeters wide, and they were aligned in a way that each was displaced between 2 to 3 millimeters relative to the other one, so that they could better follow the contour of the marble milling tooth itself. Now here, you can see the welding parameters for each of the different passes. You see that the amperage was the same throughout the hard-facing process, whereas the welding speed increased as with each layer. It should also be mentioned that the first pass was at the bottom of the tooth, and the final 7th one was at its top. The angles, of course, were selected depending on the tooth geometry. So here you can finally see what the tooth looked like before and after the hard face, the plasma welding was performed. On the left you have the state before, and here on the right part of the left picture you can see all of the 7 welded layers. Shown in the right picture is the welding plan for the welded layer and what it should have looked like. Now, in order to determine the macro and micro structures of the surface or the welded layer, the tooth was cut longitudinally into 2 halves using a PDM machine. And the rough measuring determined that the layer thickness ranged from 3 to 7 millimeters, 3.1 to 6.4 more accurately. And here you can see one of the halves that was used. The zones denoted by 1 through 3 were used for macrostructural analysis. Now, of more importance to us was the microstructural analysis, and for this purpose, 3 sections were defined, A, B, and C. Section A, as can be seen, is located on the top of the tooth, whereas section B is also located close to the top but on the side. Section C is located in the, approximately the central part of the tooth. These sections were chosen based on the content of tungsten carbides to see how their presence would affect the amount and distribution of cracks. So here we have the results for section A. This is the section on top where the thickness of the welded layer was the lowest, around 3 millimeters, and where the tungsten carbide content was also low. So here you can barely see any of that, but you can also see that there's only a few micro cracks in this particular section. Now this is section B, where the tungsten carbides the presence of tungsten carbides is far more significant, as can be seen by the black dots, and also you can see that there are significantly more cracks and micro cracks here, and that even in some extreme cases crack fragmentation has occurred, so there is a large part of the layer, of the welded layer missing, like in the picture to the right. This can lead to much quicker loss of material and is something that should be avoided and can be prevented to an extent by applying an intermediate buffer layer, which would serve as an elastic transition between the welded layer and the parent material. Now here we have section C, which also has increased carbide content, and we can also see several cracks in here, although it doesn't look as bad as the previous one. However, here this was interesting because there were micro cracks on the border area between the parent material and the welded layer. Now we have the microstructures of section B in more detail. To the left, you can see the distribution of tungsten carbides represented by the black dots. And to the right, you can also see the cracks, the micro cracks that you form within the tungsten carbide and how they are propagating through these areas. As you can see, the weld metal here has a dendrite structure, whereas the tungsten carbides have a needle-like structure. Now this is another example of crack propagation from section B, where you can clearly see how the crack advances through the adjacent tungsten carbides, which also shows the point of this paper to determine how the tungsten carbides affect the crack propagation, and here you can see the obviously negative effects that they have. On the other hand, they greatly improve the hardness, so basically the point here is to try to find a compromise between the percentage of tungsten carbides present in the welded layer, so that they can provide sufficient hardness without resulting into too many cracks. Also, as you can see in these pictures, the cracks did not propagate into the parent material in any of the 3 cases. So, in conclusion, the application of hard-facing technology on a marble milling tooth by means of plasma welding represents a method whose main goal is to improve the characteristic of the surface layer, mainly its hardness, so that the resistance to wear can be improved. To achieve this, a welded layer with high contents of tungsten carbides was applied, and then the analysis was performed on the presence and distribution of the cracks which always result in case such materials are used. This, of course, is the result of temperature differences that occur during the hard-facing process, because the materials melt and then, due to rapid cooling, they contract quickly, which results in considerable strain levels, which in turn cause cracks to appear. The microstructural analysis of the sections determined, as I mentioned, that the cracks propagated mostly through tungsten carbides, which explains why there are significantly more cracks in the areas with higher tungsten carbide concentration, but did not, once again, propagate through the parent material. However, as we have seen, these cracks can also further propagate, which can lead to significant wear due to fragmentation and the further degradation of the parent material. As I mentioned, the strain level and the amount of cracks can be reduced by applying the buffer or intermediate layer, which serves as an elastic connection between the hard welded layer and the soft parent material, because we have seen that there is a significant difference in between the hardness of these two materials. And this layer's main role is to prevent the crack propagation into the parent material. Now, further investigation of this hard-facing method should involve experimenting on a tooth that has spent a certain period of time in exploitation. And in addition, I would probably suggest taking into account the residual stresses that inevitably occur in these situations. Thank you for your attention.
Simon, thank you very much, because the time is right, 25 minutes. Thank you very much. And now your paper is open for discussion. But please, if anyone can close the door, because it is too loud outside. Est-ce que quelqu'un peut fermer la porte, s'il vous plaît? Fermez la porte. Okay, merci. So the paper is open for discussion or questions. Please. Buttering layer is put it also with the plasma technology, or how do you put this buttering layer to increase the plasticity, the ductility of the tooth?
I think my colleague knows the answer to that.
Okay. And
we just mentioned that as one of the ideas, but we didn't go into too much detail.
Too much details. Okay, thank you.
It's not what we have done here. It's just.
This is just a proposition how
to increase
the
increase.
plasticity. Yes. Okay. And what about the shielding gas? I didn't catch. What shielding gas did you use here?
Pure argon.
Pure argon. Okay. And during the plasma welding, it was a mixture between.
The plasma gas is a mixture of argon and hydrogen, and the shielding gas is pure argon.
Okay. Okay. And who did the VPS?
No.
Who did the technology?
The technology of welding was performed by our students.
Okay.
I worked with that guy, and he did this welding, this hard-facing welding, for the purpose of its masterwork.
Masterwork, okay.
Yes.
And they did it where? In showed us in Master.
Yes.
Okay.
Yes.
Okay.
Master techniques.
So it was a good job. Thank you very much. Once again,
You're welcome.
Simon, thank you very much for the nice presentation. Now, I will ask Professor
We know that many structures used in the industry, such as aeronautic, automobile, maritime, as are plates assembled with well or screws. For the design of this plate, we may call generally to the classical concept limit analysis or incremental method. But this method or these techniques present a disadvantage that there is necessity to know the exact loading history. For this, we may call or the shakedown analysis found its application privileged because it's not need the loading history. In presence of cracks, where generally we use the concept of fracture mechanics, we have few years past make an extension of the Shakedown theorem to the cracked bodies. To formulate this theorem, let's consider a cracked elastic plastic body with the boundary condition and the loading. We assume that the solution of the reference problem is given. The reference problem differs from the original problem only by the fact that it reacts purely elastic with the same boundary condition and the same loading. The theorem's statement is we have a self-equilibrating stress field rho, which is type independent, self-equilibrating. The addition of this stress, residual stress to the solution of the reference problem don't we have no plastic flow. We have make another condition on the crack land by defining a limit of this crack land, a limit, which may let small than the critic one. The expression of the crack land limit, there is the expression, it is expressed with the initial length, M and K, where the coefficient of the air curve, resistant curve. Alpha is the fact alpha is the loading factor. To bypass the singularity of the field stress, we use the concept of block of material of Nobel, which is applied by Krager. We assume that sharp notch. We have a block. We have a block of material of Krager give reduce in function of the epsilon, which is the motion of the Newberg material. A work of Wong and Stein used this radius 10 times the grain size of the material. See, to generalize, we use this block of material equal to 5 times the grain size. So the problem to determine the factor safe, the safe shakedown factor, we consider an elastic plastic cracked plate subjected to a variable loading, P, which can vary arbitrarily in type between prescribed limits Pb and Pmax. We research alpha, the load factor, the max of the load factor, the big one, where this condition are verified. So to summarize the problem, we have finite element coupled with mathematical programming to maximize the factor alpha under the condition of no plastic flow and no little FRACT. So we use for the optimization problem the augmented Lagrangian, and we need the elastic solution of the comparison problem and the construction of the residual stress field. For this in this case, we use finite element method experiment in force, not in displacement. As a first example, we consider a plate containing crack, the length A0, weight W, loaded with P2, P1. The radius of in the crack tip is 0.82 millimeters. We have the parameter of the L group. We have the line, the critical crack line, which is 1.33 A0. We take P0, the load equal to the yield stress. For the scientific reasons, we have considered only the superior half of the plate, and we show here the adopted image and the boundary condition. We have plotted the shakedown domain, which is a safe domain, according to the line, the current line. 0.2 the weight of the plate, and we see that this domain is reduced with the augmentation of the crack length. Here is comparison with the assessment for the limit analysis and the shakedown analysis for a crack length equal to half of the weight of the plate. Here we have comparisons between shakedown, the limit analysis calculated with our program, and the analytic solution. Here we show here the variation of this loading factor with the ratio between crack length on the weight of the plate. We have calculated a stress intensity factor corresponding to the shakedown state. So we use this expression with shakedown factor, the log, and the root of P R, to have stress intensity factor, which will be compared to the fatigue threshold. Here we show that this factor, KSD, does not vary with the crack length. So we can assume that can describe a parameter of the material. So we have calculated this factor for different materials. With the grain size, and according to the grain size and the plastic flow, we have our result there. This is the value of the fatigue threshold, and this value are value of Stein and Wong determined with shakedown analysis, but not with the condition on the crack length. Knowing that the relation between the fatigue threshold with the grain size given by certain authors in the literature, we have this expression that this factor vary linearly with the root of the grain size. So this relation will be searched for the shakedown stress intensity factor capacity. In our case, the yield stress and the crack root fluctuate with the diameter of the grain. So we plot the evolution of this ratio. So we have KSD on the plastic flow limit. According to the root of the grain size, we remark that we have linear variation. Then, for our, so we have this expression. Knowing for the material which verify the voltage relation, when the yield stress varies with inversement proportionnel à la racine du grain, la taille du grain. We can say that the disparities remarked between the KSD and the KS, fatigue ratio, are due essentially to the residual stress, because in our work we take into account the residual stress. And KSD can be considered as fatigue threshold, taking into account the residual stress. And in conclusion, in this work, a new method to predict the weight of inelastic crack structure is proposed. This method presents the following advantage. the use is simple. We make only elastic assessment. Elastic assessment, the loading is variable between two limits. It can make nonlinear behavior because we consider elastic computation only on the reference problems and permit to determine the fatigue ratio. I have a second work reviews when I calculate for different mode of loading. A comparison with the value of fatigue threshold for different materials. And we found the good result. I finish. Thank you for attention.
Thank you.
Thank you very much. It was a very interesting presentation, Professor. And this work is open for discussion. Please. I understood everything that Professor Belushani told me, but I don't know if you have some questions. It's a good result.
We have some result for different material and the research.
All the materials were metallic materials.
Theoretical investigation show that for the model there is problem with micro level and macro. Because there is two parameters. There is the micro yield stress and macro. The
Local stress
and macro. This fatigue threshold have two variations. In the start, there is the plastic flow which over the evolution.
The propagation of the grain.
Later, it's the disposition of the grain. Structure. So here we have the two evolution in the same time. We can have a term which is inversely proportional and a term proportional to the energy. Two evolutions. One term is depending on plastic flow, and the other with the situation of the grain. We are working in this.
The size of the grain.
Size and disposition.
And disposition of the grain. Okay. So the microstructure. Thank you very much once again.
Center of Faculty of Mechanical Engineering evaluated. And I will show you the paper that you cannot see on the screen. Of them you may know. And I will show you the paper with the subject that you can see on the screen. First of all, I would like to thank to Mr. Mohammed for inviting me on this conference. And now, let's start with the paper. So, first of all, what we shall see in this research. Presented in this paper, as the title says, is the influence of exploitation conditions and welding technique on initiation of crack and its growth, as well as a solution for their avoidance. You will see one example. A starting vessel used in thermal power plant in Organise. Used in thermal power plant in Organise, sorry. We performed inspection on this vessel that was in service after 220,000 working hours. Also, our team had analyzed the effect that could have influence on crack initiation. The effect of previous welding technology used for connecting branches with the base of starting vessel was also analyzed as one of the possibility for crack causing. Okay, let's start with short introduction. Welding is the most commonly applied technique in manufacturing, used for manufacturing of processing equipment, pressure vessels, pipelines, but it's also used for repairing of some.
Okay, just a little bit patience. The paper is very interesting because this is the case from the industry. This is something that really happened in our thermal power plant, so Mr. Branislav will solve the problem because he is an engineer.
Sorry for waiting. What is the most commonly applied technique in manufacturing of load-bearing metals, structure profiles, or some other equipment? During welding, we must use inspection before, during, and after delivery. And we must follow the regular inspections during exploitation. It's very necessary. For this purpose, we engineer use technique as ultrasounds
magnets technique, X-rays, penetrance method, acoustic emission, etc. Now, as you may know, failure of the pressure vessels represent a significant practical problems even nowadays with all these equipments and new scientific software. But with adequate control and inspection, we can discover the crack, and with that, it can prevent further crack growth, which could lead to the final failure of machine part and cause the death. That is the one thing that we wonder. Pressure vessels are manufactured by welding, and in the service you can find the cracks that is located in pressure vessels, and they are in service. Okay, with all this inspection, correct, within acceptable limits, are back in service. Failure of pressure vessels can be divided in three. Can occur due to various damage mechanisms, and they are thrid, fatigue, and corrosion fatigue. And you can see some of them on the slide. Now, let's switch to the examples. But first of all, what is a starting vessel? Okay, we must define what is a starting vessel. Starting vessel is the part of the starting facility used in thermal power plant in the Reynolds. Starting vessel represents a vapor separator, generally, wherein the remaining moisture is removed. On the slide, you can see the vapor separator system with other circulating boiler components. So the starting vessel is the part of the facility of boiler in thermal power plants. This starting vessel that you can see is made of steel WB36. First marking that you can see on the screen is the accordance with German DIN standard. And the other one is the accordance with American standard. The basic microstructure of this steel is very bent. This steel belongs to the group of low alloy, high strength steel. And its main usage is for the manufacturing of pipelines and pressure vessels. It is most often delivered in enhanced state, which results in a fine-grained microstructure. The main alloying elements of this steel are copper and niobium. And these elements define its characteristics. On the slide, you can see the chemical composition of this steel and the mechanical properties of this steel. Now, starting vessel was made or manufactured by connecting branches
the welding method. So we must, branches were welded to the base of the starting vessel. External diameter and outer diameter of connecting branch, you can see on the slide. Their values. Okay. This starting vessel was manufactured 25 years ago. So the welding technology and welding procedure was performed 25 years ago. Then welding was performed using the manual arc welding procedure, and the root pass was made using PIG procedure with Wolfram electrode. Chemical composition of used electrodes, then you can see on the slide. Sorry. Now, let's see the working condition that this starting vessel was subjected to. We have monitored and collect data on the output of the starting vessel, 1,450 working hours. Okay. We can see the pressure and temperature values during this time, and that's approximately 59 days. You can see that the working conditions are below the design ones. Now, we extrapolated this data and obtained data for the 220,000 working hours. Okay, we didn't monitor working condition for 220,000 hours. We extrapolated this data. And you can see the values of the temperatures and pressure during this period of exploitation. You can see that the internal pressure of the vessel was above, most of the time was above 200 bars. And the temperatures in range between 350 and 400 Celsius degrees. And after exploitation time, starting vessel was inspected. Inspection was performed using magnetic technique of examination in accordance with our Serbian standard, which is the accordance with ISO standard. The parameters during testing or examination, you can see on the slide. We use the device that is manufactured in England. And we examined the outer surface of the branches where the welded are done. As I said, we inspect the all welded joints on all five branches that are located in the starting vessel. And during examination, we discovered one crack. That crack was located on the branch number 5. The crack depth in the fillet weld zone was 35 millimeters, and its length was 45 millimeters. So, what we can do? We can replace this starting vessel, but that's not enough.
I forgot to tell you that this is the only one type of vessel in our part of the Europe. And the only thing we can do is the repairing welding. Repairing welding is the only thing we can do and back this vessel in service. Repairing welding was performed after inspections, and during welding we followed all the regulation and inspections were performed before, during, and after welding procedure. After repairing, our team have performed visual technique of examination, magnetic technique of examination, ultrasound technique of examination, microstructural examination, and harness testing on this welded joint. And everything is fine. So, what we can conclude from this material? Main thing, factors which affect the vessel integrity includes the choice of base materials, the choice of additional material used for welding, welding technology, choose welding technology, and exploitation conditions. We have to consider all these things. Detailed analyzed revealed that the crack most likely did not occur due to exploitation and thermomechanical load, but was probably initiated due to residual stresses at the welded joint between the riveting opening, or it is overseen during previous welding technology inspection. That was 25 years ago. Hence, we recommend more inspection, strict regulations, and not like we just saw. This is performed 2014, and the next inspection was performed, I think, in October 2016. I'm not sure. And everything's fine. So with the regular inspections, we can avoid a catastrophic failure. And that would be all. Thank you for your attention.
Thank you very much, Branislav. In spite of several problems that you had,